Hi there, folks, and welcome to this week's episode of Down to Earth. I'm Eric Edelman, your host, and let me tell you, it was so tough to figure out what to talk about for this week's show. I mean, last week was the Summer AAS American Astronomical Society meeting, and this is when all of the cool astronomers they go to one spot, and in this year's case, San Diego, or seeing the beautiful city right there. And this is where they ignored the beach in favor of talking about some space stuff in hotel meeting rooms. And this gathering is when a lot of announcements of discoveries and the like happen. So there was a wealth of topics to choose from just for this week in particular. But to be honest, way too many. There was exciting news on gravitational waves, more about that stuff, gamma ray burst, the potential multiverse, lots of just really fun stuff. And out of that smorgasbord of astronomical delicacies, today, we are going to talk about FRBs, fast radio bursts. And they are exactly what they sound like, a really quick burst of radio waves. But first, before we get into FRBs, let's go through a quick refresher of what radio waves are. And so radio waves, they're part of the electromagnetic spectrum. And the electromagnetic spectrum is all the wavelengths of light that are possible for us to see that are emitted at any place in the universe. These include wavelengths of visible light, they're X-rays, they're gamma rays, there are radio waves. And what makes one different from another type of wave is the wavelength. And that wavelength is tied to how energetic that wave is. The shorter the wavelength, you're going to have a lot more of an energetic wave, like the gamma rays. And then you get a little bit longer, you get into the visual wavelengths, and then into the infrared. And then some of the longest wavelengths out there are tied to radio waves. And so when we think, though, of things like visible light, that's part of the electromagnetic spectrum, we think of something that we can see. And that's the part of light that we can see, is visible light. And then on the other hand, we have radio waves, and when we think of radio waves, we might think of sound, something that we listen to. But that's just how we are able to manipulate radio waves. Like, for example, AM, FM radio, like we're seeing an image here of radio waves being put into different sections. So what radio is, it's either amplitude modified or frequency modified radio waves. And so that means that they can adjust the amplitude, either the height of the wave or the frequency, how fast the waves are coming to you, which you're able to, at the other side of your radio, interpret as your talk show radio or your pop tunes, whatever it may be. So it's a part of the electromagnetic spectrum that we use in really unique sort of ways. And so these radio waves, they're part of this spectrum, and we can use them like antennae and for satellite dishes and telescopes to get information from these waves. And just like we use these waves to communicate with ourselves here on Earth through the radio, things like that, we can also search for them coming toward us from distant parts of the universe. For example, there is the Parkes Observatory Telescope in Australia. We're seeing that right here. And it uses a 210-foot movable dish. That giant dish is about 210 feet, and a 59-foot antenna to search for radio waves from its spot in New South Wales, Australia. And so radio telescopes like this one, they have to be so much larger than the telescopes that we're used to. Like you might have just a portable telescope that you can use to look at visual wavelengths of light, something close to that. And it's because the wavelengths that we're looking at in the radio, they're just so much longer than the visible wavelengths. So we need really very much bigger telescopes to see what we're trying to look at there. And this telescope has actually been around for decades, this particular one. It was even used to broadcast the moon landing live. It was assisting with that by receiving radio signals from the Apollo mission. So it has a lot of astronomical history to this telescope in particular. And since 1998, the telescope has been detecting FRBs, fast radio bursts, where there is this detection of radio waves that only lasts for a few milliseconds. So it's very, very short burst of radio waves. But interestingly enough, astronomers were able to put these FRBs, these fast radio bursts,
into two separate categories. And certain FRBs, they were saying, were really astronomical in nature, really far away from us. They know they did not originate anywhere close to where this telescope was. And then there were other sources that seemed to be coming from a little bit closer, maybe even on our very own planet, as it were, sort of like it was coming from inside the house. Astronomers called these strange FRBs perytons. And the word actually comes from Borges' book of imaginary beings. So here we have a visual of what a periton is like. It's a stag bird hybrid-like creature. And so astronomers were thinking that perytons that were some amalgamation, something that they were used to. And for over a decade, observers at the Parkes telescope trying to figure out where are these perytons, where are these weird fast radio bursts that weren't seeming to come from outer space, where exactly they were coming from. And there were a lot of different possibilities being thrown around, stuff like lightning or signals from aircraft. But finally, in 2015, that's when this mystery got solved. So they started actually to look closely at the data that they were receiving, and strangely enough, these periton signals were all tending to peak right around lunchtime, right around noon. And a little further investigation took the group to their on-site microwaves. So apparently there were some folks at the Parkes Observatory site that were microwaving their lunches, and they were opening the microwaves a little too early, a little bit before the ding goes off. And with the microwaves opened a little too soon, a little radio pulse was let out. And that pulse, which is similar in nature to the astronomical FRBs that the telescope detects, happens when the magnetron, that's what it's called, within the microwave turns off. It just lets out a pulse. And so when people open the door early, that pulse can come out of the microwave. So the magnetron is sort of the thing in your microwave that generates radio or microwaves heating up that food. So because people were opening the door a little too early, they were sending out their little FRBs to the Parkes telescope. However, the perytons were only some of the FRBs, so it wasn't all just originating here on Earth. It wasn't all just something we, as our own species, had made up. And so other fast radio bursts were coming from outside the house. For example, astronomers looked back on some of the data taken with the Parkes telescope and found an FRB from 2001, and that was definitely not coming from Earth. It actually seemed rather like it was coming from a source billions of light years away. So really, really far away from us. Definitely not in anybody's kitchen nearby. And the strange thing about a burst like this is that it did not happen again. It did not happen with any sort of regularity. As far as the telescopes measured, this was the only time they were able to find it. So unlike the perytons, which were coming from the microwaves that were happening sort of regularly at lunchtime, this had no regularity to it. It was a one-time event. And so, like, it was something that happened once, some event way out there that was just sparked it, and then it was all done. So probably not distant aliens regularly using their high-powered microwaves and opening them early and giving us distant intergalactic perytons or something like that. So radio telescopes from around the world, they'll actually pick up signals like this. And they're just usually one-time events. For example, the Green Bay telescope in West Virginia in the USA, here we're seeing that, the largest radio telescope with steering capability in the world. This telescope detected an FRB in 2015 with a source expected to be 6 billion light years away. So still, again, really, really, really distant stuff. And a handful of cosmic FRBs, or fast radio bursts, have been caught by radio telescopes around the globe, but astronomers have not been able to narrow down precisely what is the source of these bursts. So seeing them in different places, seeing them as distant things, but not being able to tie them to any sort of astronomical phenomena that we're familiar with. There are a couple of thoughts, though. There's just a couple suggestions put out there that people are testing, trying to see if they'll work. And all of them are really incredibly dramatic and violent. Like one possibility is that they could be related to, say, gamma ray bursts or black holes colliding, things like that. Or if you want to know more about gamma ray bursts, I might recommend checking back on some of the older Down to Earth shows. I believe it is episode 2. We talked about gamma ray bursts. So that's something that you're welcome to check out if you're interested in that subject and haven't seen the show already. But yeah, here's a artist's conception of a black hole. And a lot of the talk about what FRBs, fast radio bursts, could be coming from does come back to things like black holes, really intense pulsars, magnetars, colliding neutron stars, just really intense, violent episodes in our universe. Here, I believe, is 2 pulsars colliding to become a black hole. So just really violent events. And so, but at the same time, these are things that they'll happen once, like those 2 pulsars, they'll collide and they'll become a black hole, and that will be it. So that's one thing that we think, hey, maybe this is a one-time event, and that's why we only see one FRB, and then it's completely done. But to add to the confusion here, the Arecibo telescope in Puerto Rico, the largest single-dish telescope in the world at 1,000 meters, or 1,000, and it detected 11 fast radio bursts over the past 4 years coming from a very particular source in Auriga. And so maybe some FRBs do repeat, possibly. And so we're thinking that maybe they come from different types of sources. Maybe all FRBs are not created equal. That could be a possibility as well. But one thing that astronomers do agree on is that they are occurring due to powerful events that are very, very distant from us. Exactly how distant is currently up for debate, but they're definitely happening in places far beyond Earth, far beyond the reaches of, say, our very own microwaves. And perhaps they're coming from nearby galaxies, say like NGC 6946 or the Fireworks Galaxy. We're seeing that coming into us live here on the Slooh telescopes. This is a galaxy that's way distant from the Milky Way. It's 18 million light years away from us, but I suppose in terms of galactic terms, it is relatively close. And so maybe there's going to be an FRB that we find in this galaxy, because this is one galaxy that we've actually seen a lot of supernova go off, about 9 in the last 100 years. And so since there's a lot of activity going on, maybe there's some activity that for whatever function that FRBs come from, maybe that'll happen. And we'll get to see an FRB from that galaxy one of these days. Or maybe most of the FRBs will come from more distant, even more distant, brighter objects like the distant quasars, billions of light years away. And so we're actually seeing, this is a live image from the Chile Slooh telescopes of quasar 3C273. So really distant, really bright galactic center. A quasar is something with a huge, supermassive black hole at its center that's just very active. Lots of stuff is happening. So maybe we could see FRBs from objects like that as well. 3C273, which our producer Trisha Ennis has nicknamed Carl, just to give it an easier name. Carl is in the constellation of Virgo, 2.4 billion light years away. And so earlier we were finding some FRBs that were coming to us multiple billions of light years away. So maybe this is in the sort of distance that we would find FRBs. Maybe this is a place that an FRB could come from. And if we're able to figure out where the FRBs or the fast radio bursts are coming from, and they are indeed coming from such distant sources, perhaps maybe those FRBs will help us probe deep into the depths of the early and distant universe. Maybe this will become another measuring tool that we can use to better understand the cosmos. But even though we're talking about distances on the scale of millions and billions of light years here, there is a way that the FRB really does shoot close to home. Remember the peritons? The FRBs that we found were our own fault, that were coming from our own microwaves. So the thing I find amazing about this is that peritons And cosmic, the distant universal FRBs are in many ways very, very close relatives, very, very similar to each other. The signal of a periton is extremely similar to that of an FRB coming from a long ways away. And the difference between the two is that the periton is a much weaker signal, but is coming from close by, whereas the cosmic FRB is an intensely strong signal coming from a long ways away. It's actually really similar to the sun and the moon in our night sky, because we see the sun and the moon, they're actually look to be similar sizes, to be similar objects. But the moon is 400 times closer to us than the sun is. Well, the sun is 400 times larger than the moon. So because of this incredible relationship they have between size and distance, they look to be about the same size. We're experiencing a similar phenomenon with the peritons and the distant cosmic FRBs. Even the ones that we're making ourselves, they're weaker and closer by, versus the cosmic FRBs. They're stronger and further away. But when we sense them, when we detect them in our telescopes, they seem to be making very, very similar signals. So, in a way, us, when we microwave our own food and take it out a little too early, we're behaving like some of the most violent cosmic events in the distant universe. We're the same. I mean, our scales are different. I'll give you that, but we're the same. We're related. And the universe is big and vast and unreachable to us in some ways, but in others, it's right there. It's we're a part of it. And from microwaves to colliding black holes, that's us. That's right where we are. And so we're still on the lookout for the source of some of these FRBs. If they tend to be all be coming from the same source, or if they're different types of FRBs, we'll very soon find out, I'm sure. But we are getting closer to that answer every single day. And the question that I want to leave you with today is there something that you do in your daily life that makes you feel closest to the stars? Is there something that you do in your life that connects you to the universe? And what is that? And if you're watching this live on Slooh, maybe let us know what that is. You're welcome to use the chat box. If you're watching it live, you'll see the chat box either to the right of this live video or beneath it. Just scroll a little bit down, depending on how your browser is working. And with that all being said, though, thank you again so much for watching this show here tonight. That's it for today, and I hope to see you here again next Tuesday, same time, same place, for another episode of Down to Earth on Slooh.com.